Hi guys, welcome to another Learn Electronics Repair video. In this video we're going to look at MOSFETs. So this is all you need to know about MOSFETs to fix stuff. Before you watch this video, I would suggest, if you haven't already seen it, that you watch all you need to know about transistors to fix stuff, because we're going to start by comparing a MOSFET with a bipolar transistor. A MOSFET, in fact, is a type of transistor, and MOSFET stands for metal oxide semiconductor field effect transistor, which is a bit of a mouthful, so we'll call them MOSFET. MOSFETs are quite analogous to transistors in some ways. So with transistors you have two types, NPN and PNP. But with MOSFETs, although we have the equivalent of NPN and PNP, we actually have four types. So let me explain to you what we have first. We can look at the differences between field effect transistors, MOSFETs, and bipolar transistors. And then we can look at how to test them with our multimeter or component analyzer. And lastly, we can have a look at what goes wrong with them normally and how we can test in circuit. So the first thing we need to look at is some schematic symbols for MOSFETs. So you may well know, bipolar transistor, we have NPN, like so, and we have PNP, which you can draw this way up. The difference being the way the arrow points, and the pins are the base, collector, emitter. And I drew this one the other way, so base, emitter, collector, and it'll come clear why I drew it the other way in a minute. The equivalent of an NPN transistor is an N-channel or N-type MOSFET. The symbol for your N-channel MOSFET is like this. And we can put a circle around it. And we have the three pins. We have gate, we have drain, and we have source. And these are basically analogous to the pins. So the drain effectively is like the collector of a transistor, bipolar. Source like the emitter. Base is like the gate. There are a few variations on this symbol. The gate connection can be the other way up. Usually is, in fact. So usually this would go such a way. But it really isn't important. So we can have this sort of symbol. And we can also have a symbol like this one, where the gate connection is actually shown in the middle. So we have again. One thing you might notice, and I always found a little bit strange, is with an NPN bipolar transistor, the arrow is pointing outwards from the circle. But with an N-channel MOSFET, it's pointing inwards. It's the opposite way around. At first, you might look at this, and because it's pointing inwards, think it's a P-type. It's just something you need to get used to. So these are N-channel MOSFETs. Whichever symbol you prefer to use. With a P-channel, it's much the same apart from the direction of the arrow. So I'll just draw the one. But again, we can have the various variations of this. And now the arrow actually points the other way, outwards, which again to me is a little bit strange, if you like. Drain, source, gate. So those are the symbols for your bipolar transistors and for your MOSFETs, and these are P-channel or P-type MOSFETs. I'm sure I don't have to draw the two versions because you can see what they would be like. You will also find that MOSFETs and bipolar transistors can look basically the same. So the same package, the same encapsulation, can be used for both, and it's normally impossible to tell just by looking at the device, if you don't know the part number, whether it's a bipolar transistor or a MOSFET. I'll give you an example. So these are a transistor, a power transistor 2ST2398, and you'll see 100 volts, 100 volt rated collector to base, 6 volt base emitter maximum, 2 amp. And you can see the devices, and this is what they look like. Now these are MOSFETs. So this is an N-channel MOSFET, 50N06, drain source 60 volts, very similar to the rating we have here. Voltage gate source is 20 volts, and I'll come to this in a moment. These are maximum ratings, by the way. And you will see this can handle 50 amps compared with 2 amps, but physically they look the same. So as I mentioned, it can be very difficult just by looking at a device what it actually is. We can look at them with a test meter, and that even with a multimeter we'll be able to tell the difference from one to the other, or we could use a component analyzer. But we'll come to that a little bit later. Now let's have a look at the things that are different between MOSFETs and bipolar transistors, rather than the things that are basically the same. MOSFETs and bipolar transistors also have the equivalent uses. So they can both be used either as a switch or as an amplifier. The first major difference between your MOSFET and your bipolar transistor. A bipolar transistor is a current controlled device. So the current flowing from the base to the emitter will control the larger current flowing from the collector to the emitter. And the ratio between the control current, the base current, and the collector current is called the gain. And for reasons I said I didn't know on the previous video, for which I was chastised, gain is actually called HFE. And I'm going to tell you now why it's called HFE and not, for instance, G or GA for gain. And HFE actually stands for hybrid parameter, forward current gain, common emitter, and even after I look it up. I'll defend myself for not knowing what it stood for. The reason being, because I don't need to know. Okay, I'm not a circuit designer. The HFE is the gain as far as I'm concerned. And the only time I really need to know it is if I have some fault condition where I have a problem because the gain is too low, and my component analyzer will tell me that. But besides, we're talking about MOSFETs today, so let's look at the differences. The bipolar transistor then is a current controlled device, and it will have a gain which is expressed as HFE, which effectively is the number of times the collector current is than the base. So for example, if the base current was 2 milliamps and the current here was 140 milliamps, that's a gain of 70. So that's what it is. Your MOSFET, however, is a voltage control device. It works in the same way, if you like, but instead of passing a current through the base emitter to control the current, with this you just apply a voltage to the gate. Now, on a bipolar transistor, the input resistance of the base emitter is low. The input resistance is low. This is why we need to connect resistors like so on our transistor when we apply a base voltage. Otherwise, because the resistance is low, it will just pass a massive current through the base emitter and burn the junction out. The transistor will fail. In the case of a MOSFET, you can actually connect the gate directly to the drain voltage, as long as you do not exceed the maximum parameter. So in this case, the maximum voltage between the gate and the source would have to be less than 20 volts. So you can't take this above 20 volts. If you imagine this is connecting to your ground, 20 volts is the maximum. That doesn't mean to say it takes 20 volts to turn the MOSFET on. Most MOSFETs will switch on, or at least start to conduct, with a gate voltage of about 2 volts to 3 volts. Once you get to this voltage, it starts to conduct. But unlike the transistor, where the base emitter voltage cannot go above around 0.7 volt, otherwise it would destroy the device. In this case, you can continue to increase the gate voltage. It will reach a point where it's saturated, maybe at 4 volts, 3.5 volts. It cannot turn on any more, but you will not cause a problem by increasing the gate voltage further until you reach the maximum rating. And you can find that from the datasheet. So your MOSFET is voltage controlled, and the input resistance is high. The gate is effectively an open circuit. With a transistor, your base current is going to be in the range of microamps into milliamps. With your MOSFET, the gate current is going to be practically nothing, in the picoamps range. It's probably so low that without special equipment you can't even measure it. So this, if you're thinking about it, may beg a question. Why do we have resistors on the gate of a MOSFET if effectively it's like an open circuit, so no current can flow from the gate to the source? Well, the reasons for that I'll come to a little bit later. But for now, and I will come to it, let's just carry on where we're going. We'll put this question on one side and I will answer that for you. For now, let's continue with the differences between the bipolar transistor and the MOSFET. So, another difference, relatively speaking, your bipolar transistors, switching speed on to off is slow. It takes an amount of time for the base current to the emitter to start flowing or stop flowing, and that limits the switching speed. With your MOSFET, the switch speed is fast. This is because you only need to apply the voltage, no current needs to flow. Although, technically, again, I'll talk about resistors. So we have that difference. And the last main difference is that an NPN or a PNP transistor are unidirectional. So the current flows one way between the two, okay? In the case of your PNP, it's emitter to collector. In the case of your NPN, it's collector to emitter. They're unidirectional. A MOSFET is bidirectional. So when you turn a MOSFET on by applying voltage to the gate, current can flow in both directions. That is the basic differences between bipolar transistors and MOSFETs. With a P-channel MOSFET, just like the PNP transistor, the gate voltage has to be below the source voltage. It needs to be negative with respect to the source to switch the MOSFET on. But this does not mean that you need a negative voltage supply to switch on a P-channel MOSFET. And this can confuse people, so I'll just explain it to you. A typical circuit, so this is with an N-channel MOSFET. We have the gate, drain, source. We can connect this to ground, and we'll connect this to a load. Well, let's put a light bulb here. Little light bulb. And this to a positive supply. To switch the MOSFET on, I'll just complete the symbol. I won't be lazy today. There we go. To complete symbol. Okay. So to switch the MOSFET on, we need to apply a positive voltage to here, and this could be 3 volts, 4 volts, something in that region. It will turn on. So we can take, for example, from here a resistor to the positive supply, and we can take a switch to ground, and we can make this quite a high value resistor, 10k or something. So when we close the switch, we ground the gate and the thing switches off. Yeah. When we open the switch, this resistor pulls the gate voltage high. It goes above 3 volts. In fact, it will go up to the supply voltage, and it switches on. And that's how it works. And that's quite intuitive. With the P-channel MOSFET, we need to think of it like this. So just like the PNP transistor tends to be used this way up with a positive voltage rail here, this is much the same. So we now have our P-channel MOSFET. We'll put the load. No, we'll put it here. Let's put it here. We have our P-channel MOSFET. Our symbol, and here we can put our light bulb, and we can go to ground, and this is a positive supply. Now if we connect the resistor here, so this is your source, this is your drain, this is your gate, the other way around, yeah, this is your gate, this is your drain, this is your source. With the resistor holding the gate voltage up to the source, this is switched off. To switch this on, we simply have to take the gate voltage through our little switch to ground, as long as the maximum voltage doesn't exceed the voltage gate source. Let's say we have a 12 volt supply, we can do that. Otherwise we would use a resistor in here. But again, in this case, we close the switch, the gate voltage comes down and the light turns on. But notice we only have a positive supply, there's no negative voltage. We're just making the gate voltage to be lower than the positive supply. For example, if we have a resistor in here, and depending on the values of the resistor, the voltage here could be 12 volts, the voltage here could be 8 volts. Put the resistor in, and again we'll have our little switch in the circuit. So when we switch the switch on now, because of the ratio of the two resistors, this goes down to 8 volts. It's now 4 volts negative compared with the source. It turns on, but notice there's no negative voltages. If we put our multimeter between here and here, we'll see 8. If we put our multimeter between here and here, we'll see 12. Yeah, positive voltages, but the gate is lower than the source. Once you get your head around that, you'll find that PNP transistors and P-channel MOSFETs become quite simple to visualize how they're working. Now let's have a look at some MOSFETs with our multimeter. So we're going to put the multimeter onto diode range, and this is one of the N-channel MOSFETs that we were looking at earlier. We have on this MOSFET, and I will just draw it out so we can see what we have. We have gate, drain and source, and this is quite a common layout for MOSFETs. We'll also have a P-type of MOSFET, so we have one here. This happens to be a surface mount one. So the tab is the same connection as the middle pin, which is cut off basically. So here we have our P-channel MOSFET, little tab on it, a short leg, 2 longer legs, and again we have the same layout: gate, drain, source. They don't have to be this way, but this is a very common layout for MOSFETs. Let's check them with a multimeter. So we'll take our meter and we will first measure between the drain and the source. This is the N channel, N type, and this is the P type. save any confusion with what we're doing. Okay, so with the N-type, let's have a look between the drain and source. So with the positive to the drain, which is how it would normally be used in a circuit, to the source as open circuit. Okay, drain source as open circuit. If we go the other way round with a negative to the drain, you'll see it reads like a diode junction, and I'll explain this in a moment. Now, if I touch the gate with the negative lead compared to the source, nothing happens. Okay, the transistor is just switched off, and I caught the wire and I did it too soon, but you saw what happened. So with the negative connecting to the gate, it's turned off, but we know that the MOSFET needs a positive voltage on the gate to turn it on. So let's go from the source to the gate, touch it. Yeah, now watch what happens. It's now turned on. Yeah, it's like a short, and it's bi-directional, and it stays turned on until I touch the gate with a negative lead, and then it goes back to being open circuit and like a diode junction. Why is it doing that? Well, first of all, our tester is actually applying a voltage to the gate. If I take another multimeter on volts range, you will clearly see that is the case. Here is my fluke meter on voltage range, and this is on diode mode. So let's see. So we connect the two reds together and the two blacks together, and you can see that the multimeter in diode range is putting out 3.9 volts. This tells you it's supplying enough voltage to turn on the gate of the MOSFET, which is why the MOSFET is turning on. That's why it turns on. It should also tell you, by the way, if you're worried about the low ohm short circuit finder we looked at on the previous video, and you're worried that like a high voltage of 3.9 would damage graphics cards and such like that work on 0.8 volts, can I ask you why you never worry about using your multimeter on those cards? But that's just to prove something else we were talking about. It's nothing to do with this video. So we can see why the transistor turns on, because we apply a positive voltage to the gate compared to the source. Positive to the gate and it turns on. The question is now, why does it stay turned on? Why does it not only turn on when there's positive voltage on the gate? Because there isn't any now. Yeah, I've taken the meter off, there's no positive voltage on the gate. Why is it still switched on? Yeah, until we put the negative on the gate. Well, the reason for that is actually quite simple. Your MOSFET, basically, the gate acts like a capacitor. So, when you connect your positive meter lead to here, effectively this is a capacitor internally in the gate, in the MOSFET. And when you put your meter lead from here to here, here's our meter with the leads. When we do that, we charge the capacitor up. So what happens now is the capacitor holds the charge. When we take the meter probe away, there's nothing to discharge. The capacitor, it stays charged up. Therefore, the MOSFET stays switched on. And that is very, very important when it comes to fault finding and the problems we can have with MOSFETs. So just remember that. It's like a capacitor, and that's the N-type. And the P-type is the same, just back to front, if you like. So with the P-type, this is the gate. If I go between the drain and source in one direction, I read like a diode junction, which we'll come to in a minute. In the other direction, I read nothing, it's open circuit. If I now put the positive lead on the gate compared to the source, yeah, I've touched it with a positive lead. This still reads like a diode junction. It's still reading diode junction in one direction and open in the other, because it's a P-type. Let's put the negative lead on. So now the gate is below the voltage of the source. Now let's see what happens. See, it's switched on. It's 0 in both directions. And it will stay switched on until we apply a positive voltage, or we short the gate back to the source and we discharge the little internal capacitor. Yeah, it's back to being a diode junction again and open circuit the other way. That is how you test MOSFETs with a multimeter. Now, the question is, why do we see a diode junction in one direction between the source and the drain? Well, the reason for this is because this isn't the complete symbol for a MOSFET. The actual symbol for the MOSFET, and I'll have to redraw it so I can fit it all inside the circle, is like so. This is the N type, N channel. Okay, and we have from here to here a diode internally. Drain source gate. And likewise for the P type, it's exactly the same thing. So we have again the MOSFET, arrow obviously pointing the opposite direction, the gate, but the diode is still in the same direction. And this is where I made a mistake. So I'll just correct this and then we can continue. So the first image, which was this one, this is actually correct, and this image is for an N channel MOSFET. So we'll just try it right on the screen. That's your N channel. Okay. The P channel, actually the diode goes the other way round. So we'll just correct that one. That's here. So I get to the right place on the screen. So okay, so the diode actually in this one goes this way round. First time I've played with this particular toy, so we can just draw it in there, and we can put a circle around it as well. Okay, so now we still have the source and we have the drain pin, and of course we have the gate here, but the diode is the opposite way round. And this is your P channel. So you might wonder, why did he put a diode inside a MOSFET? Well, the answer to that actually is that they don't. This diode is basically there because of the way the MOSFET is actually made. So this is called a parasitic diode or a body diode. And what you're actually seeing is the PN junction between the two layers of silicon, P-type and N-type, that make up the MOSFET. So now we know why there is a diode junction inside our MOSFETs. Let's continue. Now you might wonder, why do they put a diode in the MOSFET? And you also might wonder, if you know anything about buck regulators and circuits that are switching relays and inductor coils, is it there to take away what's called the back EMF? Well, the answer to the first question is they don't put a diode in the MOSFET. The diode is there because of the way that the MOSFET is constructed. It's a byproduct of the construction of the MOSFET. That's why the diode is there. It's not deliberately put there. It's just a byproduct of what the MOSFET actually is internally. And the second question about, is it there to stop EMF damaging the MOSFET when an inductor switch is off? The answer is no. And I have to just interrupt this again. That is not what the body diode is there for, even though Google will tell you that's exactly what it does. Yeah. Well, it doesn't do that, and I'm now going to show you exactly why it is not doing that. But if you look at the circuit for what you were thinking, okay, you were thinking of something like this. Round, gate, inductor coil, yeah. The diode, if you think about it, which is in here, is actually in the wrong place. the diode you were thinking about actually goes here. Okay. If that's beyond some of you guys, by the way, I did a whole video on inductors, all you need to know about inductors to fix stuff, and if you watch that video you'll understand what I'm drawing here. But for the rest of you who know about that, can you see now that diode is not that one, it's in the wrong place in the circuit. Let's just have a quick talk about why do we need a gate resistor on a MOSFET or gate resistors. Okay, why do we have the gate resistors? Well, the reason is down to the fact that this acts as a capacitor. So if you were driving a MOSFET just as a switch, effectively just switching it on and off, the capacitance isn't really a problem until you get to high frequencies. So a capacitor passes AC but blocks DC. When you get to high frequency switching, that capacitor becomes a load on your switching device. So if you have some sort of driver sending pulses into here, the capacitor will effectively be charging every time you get a pulse and putting a load on the signal. And what that will tend to do is cause the signal not to rise straight up, but to rise up slowly as the capacitor charges. And end up with something like this, which is probably not what you intended. So the resistor is basically to limit the current that's charging the capacitor. And these capacitors are, by the way, they may be 2000 picofarads, something like that sort of value, which is about 2 nanofarads. You know, it's a couple of nanofarads, that's the value. This will depend from one MOSFET to another, and the datasheet would tell you. So the idea of the resistor is to effectively limit the current this is passing by switching on and off. You can probably realise the higher the value of the resistor, the longer it takes to charge the capacitor, so the slower the switching speed, but it puts a lower load on whatever is driving it. That is a matter really for circuit designers. It's not for us. We just want to fix the stuff. But I thought I would just mention, if you've always wondered, why we do have gate resistors on MOSFETs. Does a MOSFET have gain like a transistor has gain when it's used as an amplifier? And the answer is it doesn't in the same way, because there's no gate current, there's no current flowing, so there is no current gain. But what a MOSFET does have is a parameter called Rdson. And this is the resistance between the drain and the source when the MOSFET is turned on. I was just testing some with a multimeter, you saw, and I was reading effectively 0 across the MOSFET. But in actual fact, they don't have a resistance of 0 when they're turned on. But it can be very, very low. It can be into the microohms or tens of microohms. So to find a MOSFET with an RDS on of something like 20 microohms, or milliohms rather, is not unusual. Milliohms, I'm saying micro, it's milliohms. So RDS is effectively the resistance when it is switched on, and it's a very low resistance. So your main important parameters of a MOSFET is how much voltage can it withstand, how much current can it pass, how much wattage can it dissipate, the RDS on should be low, and the gate capacitance. That's the main parameters that affect the performance of a MOSFET. This can become quite important, especially in amplifier circuits. So when we're looking at amplifier circuits, and also sometimes in switching circuits where we have many MOSFETs in parallel as a pulse width modulator, so they're all sharing the load, then these factors all have to be balanced. We can read some of these using a component analyzer. So let's have a quick look at our MOSFETs with the peak analyzer. Let's see what it tells us. This is our N-channel MOSFETs. I'll just switch the analyzer on. Let's connect the cables to our MOSFET. We'll put the green on the gate, why not? Green for green, gate for gate, the two G's together. But it doesn't matter. The analyzer really doesn't mind. What's it going to tell us? Enhancement mode, N-channel MOSFET. And we'll come to an enhancement in a moment. It's telling us which pin is which. The gate threshold, so this is the voltage at which it turns on. The test current. And that's basically giving us those parameters. It's not telling us the RDS on. It's not telling us the capacitance of the gate. There are analyzers that will, and that becomes more important when you're trying to match transistors and amplifiers. I don't at the moment have a tester that will do that, although maybe we could build something. So we'll look at our P-channel MOSFETs. So again, this is the gate. I put the blue wire on it. This is the source, and then the drain is the actual metal tab or the middle pin, which is short, but I think I can get. Yeah, I'm on. Let's see what it's told us. Enhancement mode P-channel MOSFET. Again, tells us which pin is which. Voltage threshold, slightly different. The test current. The component analyzer was telling us something interesting, that these are enhancement type MOSFETs. And this leads into what I was saying, that there are actually 4 types of MOSFETs. And these ones, the enhancement type, are the most common. But we also get a depletion type or depletion mode MOSFETs. And again, they come in P-channel and N-channel. So with a depletion mode MOSFET, this is a symbol. I'll just put the arrows in. So again, this is a P-type. Gate, source, drain. And we'll have the N-type as well. So we'll just do the other one. Gate, drain, source. The difference between an enhancement and depletion type is effectively they are opposite. So with the enhancement type, you have to put a voltage on the gate to turn it on, either positive or negative with respect to the source, depending if it's P channel or if it's N channel. And that's what we've just been looking at. With a depletion type, it's the opposite way around. So with no voltage on the gate, the MOSFET is switched on. It reads effectively 0 ohms. And to switch it off, you put a voltage on the gate, either positive or negative, N channel and P channel. So that is the difference. Now the depletion type MOSFETs, depletion mode, are not very common. So much so I don't actually have one here. You will find them in some type of circuit, so you need to know about them. But I don't have one to show you, and I must admit I haven't come across them in anything I've been working on. I'm guessing some of you guys will be able to tell us where you will commonly find depletion mode MOSFETs. Otherwise, honestly guys, I wouldn't worry about them until you find one. And then panic. No, seriously, when you find one now, you'll know what it is. As I'm still on this page, I'll just mention something that should be obvious, but maybe isn't. Because a MOSFET has this internal diode built into it, it means that if you apply a reverse voltage between the source and drain, so in other words, the source is more positive than the drain, it will conduct. And it will conduct regardless if there's any voltage on the gate or not. The MOSFET cannot switch the current off in that direction. So really you need to think of a MOSFET as acting like a diode in one direction when there's nothing on the gate, and like a short circuit in both directions when there is a voltage on the gate. This ability of a MOSFET to be able to conduct in the opposite polarity, if you like, It's sometimes used by circuit designers, so it's something you need to keep in mind, because in some cases you cannot understand the circuit operation unless you understand the role of this diode and the fact that it will conduct when it has a reverse polarity across the source and drain. Let's have a look now at some of the things that go wrong with MOSFETs. Much like transistors, they tend to fail in two ways. They either go short circuit or they go open circuit. And like transistors again, they can go short circuit from the drain to the source, or from the gate to either, or the whole thing can go short circuit. So short circuit MOSFETs is a very common failure, and quite often as well they will explode. They will go open circuit, so they can burn up, explode. Sometimes they can look like they've exploded and still be short. But these are the main failure modes of MOSFETs. They're not so likely to fail in unusual ways like bipolar transistors do. But you can get MOSFETs that fail where the RDS on, resistance between the drain and source on, goes high. This sort of problem you're not likely to find without taking the components out of circuit. Mostly speaking, you will have these problems. The open circuit ones can be quite hard to find unless they've physically blown and you can see they're blown. The short circuit ones are quite easy to find in circuit, and normally, like just about everything else, the parts that are doing the most work fail the most often. So it's the larger power devices, the output devices, which tend to fail. Having said that, there are a number of other problems with MOSFETs that you need to know about. One of them is ESD. They're electrosensitive devices, electrostatic sensitivity basically. MOSFETs, especially vintage ones, can be damaged just by touching the gate with your finger, and normally they should be kept when they're stored in a little bit of conductive foam like this, not in a plastic bag. Anti-static bag, yeah, sure. So MOSFETs can be prone to ESD damage. When you're working on MOSFET circuits, especially in amplifiers and such like, it's a good idea to keep that in mind and try not to touch the gate when the device is out of the circuit. Once it's in circuit, then the gate resistor will effectively protect the gate from high voltage. Like I was switching it on with my multimeter, if you touch the gate with your finger and you have a lot of static charge in you, it's easy to put more than say 20 volts between the gate and the source. That's why they get damaged. But once the gate resistor is there in circuit, it really protects the device. Which brings me to gate resistors, and this is quite important. You could see that the MOSFET would turn on using my multimeter when I applied some voltage to the gate. So I touch the gate with my multimeter. I'm showing you it gives about 3.8 volts. It turns on. And when I take the multimeter away, it stays turned on because the effective internal capacitor stays charged up. This can be a problem, especially in VRMs, but also amplifier circuits and many places you find MOSFETs. If you disconnect the driver, so normally you'll have some sort of pull-up resistor, and the resistor goes to whatever device is driving the MOSFET. You'll have a circuit something like this, and this device will be connected to ground. So when there's no drive to the MOSFET, the internal resistance of this device is holding the gate low. The problem occurs when this resistor goes open circuit, and this often happens when the MOSFET went short circuit. So you've changed the MOSFET and you haven't realized that this has gone open circuit. What happens now? You might think, well, the MOSFET's got no drive, yeah, the resistor isn't there. So when I power up, it's got no drive. Well, it might have a pull-up resistor, and that will instantly cause the MOSFET to turn on. In which case, because this circuit isn't there, that MOSFET comes on and stays on, and whatever circuit it's supplying, power runs down through here and the whole thing goes short again. Okay, but even if you don't have this resistor, so you've got a circuit, we'll put something back in again, so you've got a circuit like so, no pull-up resistor, just a gate resistor going to whatever is driving it, the driver IC, pulse width modulator, whatever, and then internally that goes to ground. Same thing happens, the MOSFET was short, so you've changed the MOSFET, you found the short circuit MOSFET, you haven't realised this is open circuit. In this case, you could reasonably expect, well, if there's no drive, it can't turn on because there's no drive to the gate, yeah. But you saw yourself that any voltage applied to here stays here. It doesn't go away because of the capacitance. So it's quite likely, even because you've got other PCB tracks near to the one that you've got, and there's a little bit of interference, a bit of capacitance between them, because look, two PCB tracks, yeah, close together. What have you got? You've got a conductor, and you've got an insulator between them, a dielectric, yeah. And if this conductor is connected to your gate of your MOSFET, yeah, and the resistor that's here is open circuit, so there's nothing else connecting to the gate, it's not unlikely that switch it on a few times and the surge of current through here will induce some voltage into this, or act like a capacitor. There'll be some voltage on the gate, and this will now turn on, yeah. And your 12 volts coming into here, assuming this, for example, is a buck regulator going off to your GPU or something like that, yeah, through a buck regulator, this will turn on, the 12 volts will come down through here straight into your GPU or CPU or whatever. Doesn't want 12 volts, it wants 1 volt or 3 volts, yeah. So it's very important to understand that not only can MOSFETs fail because the gate resistor fails, but they can also fail in a way that is catastrophic to whatever is being connected to the other side of the MOSFET. So the upshot of this is that you need to check for open circuit gate resistors, especially when you had a short circuit MOSFET. One good way to do this is to do what I did. You saw me with my meter effectively going from the source to the gate and then measuring between the drain and source. So I'm using my meter, you've just seen me do it. I'm using my multimeter to turn the MOSFET on. One MOSFET. Well, let's do it again because it's so cool. One MOSFET turned off, touched the gate, one MOSFET turned on. And it'll stay turned on until we discharge the gate. That is a very cool thing to do with a MOSFET out here. But you should not be able to do that with a MOSFET in your circuit connected to a pulse width modulator. Because unless this gate is open circuit, when you apply some voltage to here, yes, if we used another meter, maybe this is switched on. But once you remove the voltage from your multimeter, the resistor, which is effectively connected from here to ground, will discharge the voltage and the MOSFET will switch off. So you should not be able to turn on MOSFETs in circuit like I was just doing out of circuit. And this is so reliable, it's something you should test. So when you've changed your MOSFET, your shorted one, try what I've said. Try to switch it on by applying voltage to the gate. And remember, P channel is the other way round. Yeah. And make sure that you can't switch it on that way. If you can switch it on that way, find the gate resistor. And if that's okay, have a look what's wrong with the driver, because it may be that when this went short, it didn't blow the resistor, but it blew this. And this is now open circuit inside. Yeah. So that's a very important point with MOSFETs. And this problem is called floating gate. Yeah. And for the same reason, never remove the driver or disconnect the driving circuit and switch the device on. You're asking for trouble, as I've just described. So can we test MOSFETs in circuit with our multimeter? Well, let's have a go. We have some MOSFETs here. This is actually a VRM for a motherboard. So this is effectively the voltage supply for the CPU. And these are MOSFETs. Now, if you're not familiar with these, you may wonder why do they have 8 legs on them? Why is there 8 pins? And the reason is, with these, that basically 4 of them are the drain, 3 of them are the source, and the other one is the gate. So the pins are actually all connected together. If you look here, you can see, I just take the test meter. Yeah, you'll see they're connected together. They're connected together. The one that reads the resistance is the gate, and then the other side are all connected together. Okay, I'll just get a good connection like you'll see. Okay. Sometimes these devices can actually be 2 MOSFETs in one, a dual MOSFET. So that's something you need to check from the part number. But I'm sure you can see here we have 4 pins altogether, 3 pins altogether, and then this is the gate. And as I was just describing, the MOSFET should be switched off. Well, there's a diode in one direction, as we know. I'm reading some resistance, but bear in mind there's other components in the circuit. And if I go onto the gate, which is here, and then back onto the MOSFET, I should not be able to turn it on. We have the diode junction. Okay, and a little bit of resistance the other way. So this is what I'm saying, you should not be able to turn them on like I was doing out of circuit. If you can, you've got a problem. Let's have a look at some other possibly MOSFETs. I'm sorry, I just caught the meter. Okay, so we have here a lot of either transistors or MOSFETs or either diodes. In fact, actually I know from the part number some of these are actually double diodes. These W2F and WV3, I recognise the part numbers. Let's have a look for some other ones. These may be transistors or diodes or MOSFETs again, and it's very hard to tell. So we can have a look, but normally speaking in circuit you cannot tell if you have a transistor. This would be the base or gate on the red pin. Nothing there, nothing there. Go the opposite way, nothing there, nothing there between these two. Do we see a diode junction the other way? Yes. So that one I think we can say is a MOSFET because all we can see is the diode junction in one direction. But it's not a very reliable way of testing, to be quite honest, and you will find, I mean, that's the diode junction there, and is there one here? No, but again, these could be just diodes. These could literally just be diodes. So I'm sure you can see from what I'm showing you, it's not really practical to test for MOSFETs in circuit unless they are short circuit. Short circuit MOSFETs, especially in the voltage regulator modules, when you have many MOSFETs in parallel, is a topic in itself. And I made a video showing how to trace short circuits in this type of circuit, which I'll link from this one. So does this mean we can't test MOSFETs in circuit? Well, actually no, it doesn't really mean that, because we know that the conduction of the MOSFET is controlled by the gate voltage, positive or negative with respect to the source. If we know we have a MOSFET and we measure the voltage on the source and the drain, especially the voltage difference between the source and drain, then we can quickly realise whether the MOSFET should be switched on or off. And if it's switched on, then the drain and source should be basically the same voltage. So I would suggest the best way to test MOSFETs in circuit is using your multimeter in volts mode with the device powered up. And there we have it. That is not everything there is to say about MOSFETs, but I'm sure that's everything you need to know about MOSFETs to fix stuff. I hope you enjoyed this learning electronics repair video, and I'm looking forward to see you all soon on another one. So there's one thing left for me to say now, and that is ciao for now, guys.